Let us engage in mathematical discourse. 13.1, End Behavior Multiplicity. This is basically a summary and review recap of what we talked about on Friday. So this first slide is the end behavior notes. And when we're talking about end behavior, what we're really looking at is as the graph goes either forever to the left or forever to the right, what is happening to the y values. The y values have basically two options. They can go up to positive infinity or they can go down to negative infinity. And depending on the highest exponent of your polynomial, remember highest exponent is the degree. So if the highest exponent, if the degree is even, like 2, 4, 6, whatever, then you are guaranteed that both endpoints, both end behaviors are going to be either pointing up or both are going to be pointing down. Other stuff can be happening in the middle, but again, we're just talking about end behavior here. And whether things point up or down is all going to depend on this bottom thing says. We'll get to that in a second. If the degree is odd, so it's linear, it's just a regular x, or if it's x cubed to the fifth, whatever, then they'll go in opposite directions. So one end will be pointing up, the other end will be pointing down, one way or the other. Now, the leading coefficient tells us if the right side of the graph will point up or if it will point down. And that all has to do with if you have a positive or a negative coefficient. So if you have a positive leading coefficient, if it starts off as just a regular positive x to the fourth, okay, then that means that the right hand side of the graph is going to be pointing up. Well, if it's x to the fourth, it's an even degree, so both of them are going to be pointing up. Versus if I had a positive x cubed, then the right hand side is going to be pointing up while the left hand side is going to be pointing down because odd degrees point in different directions. So knowing that the leading coefficient is either positive or negative tells us if the graph on the right hand side will point up or if it'll point down. And then from there I just take whether or not it is even or odd, and that tells me if the left hand side will match it or if the left hand side will be opposite. Then multiplicity. Multiplicity seems a lot more complicated than it really is. Multiplicity just refers to how many times a root is a zero for a polynomial function. In order to really tell this stuff, you need to look at it in factored form. And from that, in factored form, you can easily tell what the different roots are. But in factored form, you're going to see things like, here, x to the fifth, or this x squared. And even important still is that there's no exponent on that middle one right there. That's going to be where the multiplicity is right there, those exponents. And that's how we can determine what the multiplicity is, because we just look at the exponent of each of the factors to tell what the multiplicity is for that root. So, in this example, the actual roots themselves, the zeros, are just, from factored form, I can tell that the zeros are just the opposite signs. So if x minus 2 is a factor, then 2 is a root, which means that we have negative 3 and we have positive 7. Those are the roots. And that has nothing to do with the exponents, just looking at the different factors, those are the roots. Okay? Now, the exponent is what tells me about the multiplicity of that root. So because of that first factor, x minus 2, because it has the exponent of a 5, then we say that the root, or the 0, whatever word you want to use, the root 2 has a multiplicity of 5. It just has to do with the exponent. And then, this middle one, it doesn't really have an exponent. Yeah, it does. It's an exponent of 1. So we just say that this root negative 3 has a multiplicity of 1. And then the same thing for this last one here, that the 7 root has a multiplicity of 2. Now, technically speaking, if you go in and you graph this function right here and you look at it in the calculator, you would see it cross or touch the x-axis at 2, negative 3, and 7. So you would only see 3 zeros. 3 unique zeros. But because of the multiplicity, we would say that it has 8 zeros total, and that just comes from adding up all of these different multiplicities. Now, well, I guess we'll explore that when we get to that problem. So let's just do a real quick end behavior question. We're going to determine the end behavior first, and then we're going to go ahead and sketch it. So first of all, I'm going to look to see the degree is, it's cubed, so that's an odd degree. And odd degrees mean that they go opposite directions, the endpoints go opposite directions. And then I just look at this leading coefficient to see that it's negative. So a negative leading coefficient means that on the right-hand side, it should be pointing down, and on the left-hand side, it should be pointing up. Why is it pointing up on the left-hand side? Because this is an odd degree. Odd degree means that whatever the endpoints are, they're opposites of each other. And since I know that the right side must be pointing down, because we're negative here, then that means that the left-hand side is the opposite. So the way that we're going to write that is that on the left-hand side, the left end behavior will be that the y values are going to positive infinity, and that the right end behavior, the y values are going to be approaching negative infinity. Now let's sketch this. So I'm going to pull up my little calculator here and type all this stuff in. Okay, y equals, we've got negative 0.2 x cubed plus 3 x squared minus 11x plus 5. Okay, taking a look at that graph, and okay, sure enough, I can see then, as proof, the left-hand side is going up, the right-hand side is going down, and some other stuff was happening in the middle, and we're just going to make a real quick, rough sketch of that. So I kind of have a little mental image of this in my mind. I'm just going to draw that real fast. Bottom line is it essentially looked a little bit like this. Okay, without being too specific, that's a sketch of that graph. See, basically the same thing. Okay. When we're sketching for this stuff, we're just sketching quickly like that. Now then, we need to factor this a tiny bit, and then we're going to state the multiplicity for each zero, and then we're going to go ahead and determine end behavior. So I say factor it because if you look at this first one, there's some common factors in there that we need to pull out. So we have a tiny bit of work before we can state the multiplicity. You really do have to have it in completely factored form in order to tell what the multiplicities are of your roots. So looking at both of these terms right here, I notice that 3x is a common factor. So I'm going to pull out the 3x. And if I pull out 3x, then inside here I'm just going to have an x and a minus 2. And then I still have this other factor that was, this thing is fine. So now I can look at all of this and I can determine, first of all, what the roots are, and then what the multiplicity for those roots are. Well, there are basically 3 factors here. There's this 3x, there's this x minus 2, and then there's this x plus 4. Well, the 3x, it's not plus or minus anything, so then that means that the 0 from that is actually 0. For this middle one, it's just the opposite sign, which is going to be positive 2, and for the last one, it is the opposite sign again, which is negative 4. Now then, we have 3 roots, 3 unique roots. Their multiplicities would be, for the first one, the exponent of this x is a 1, which means it's a multiplicity of 1. Let's just say here, m equals, the multiplicity is 1 on the first one. On the second one, again, the exponent up here is a 1, so that multiplicity is a 1. And this last one, the exponent's a 2, so that multiplicity is a 2. Pretty simple, right? And now we want to determine end behavior. Well, this is going to be a little bit tricky, especially since in order to really see what this entire equation would be, is I'd have to FOIL it all out. We don't actually have to do that because end behavior only cares about one thing. What is the largest degree, the highest exponent, and what is the coefficient for that thing? So if all I do is focus on just taking the x's and figuring out what's the maximum x squared going to be and what would the coefficient be for it, I can do that pretty simply. Like right here, because this thing's squared, I know that that's going to make an x squared out of this whole little part right here. So I know I have an x squared here, I have a regular x here, and x squared times an x would be an x cubed, and then times this 3x would be 3x cubed, or to the fourth, 3x to the fourth. Alright, well that's all I needed to know in order to tell end behavior. So from that information alone, I can tell that because it's positive, that both ends are going to be pointing, well the right end is going to be pointing up, and then because we have an even degree, both ends are going to go the same direction, so this thing is virtually going to look like pointing up on one side and pointing up on the other side as well. Again, even degree, both endpoints will point up the same direction, positive coefficient, they're both going to be pointing up then. And technically that's all it is for this question, but I want to go ahead and share one last thing about multiplicity. What other important things you see from it. Depending on if your multiplicity is even or odd, then the graph will either cross the x-axis or it'll just touch it and bounce off of it. So for these first two things here, at 0 and at positive 2, because their multiplicity is odd, these would actually cross the x-axis. But then this last one, because its multiplicity is even, at -4, if you were to graph this, you would see it bounce off of the x-axis. So I'm going to just show that real fast, just showing that the actual aspect of it crossing or bouncing. I'm going to type in the original problem here. 3x squared minus 6x, and then times x plus 4 squared. Now the graph will probably be a little bit crazy looking here, right? Okay, we can't really see a whole lot on this thing, but what we can see is that, actually, what's funny? I'm gonna adjust the window because we actually can't really see something important here, and it would be very important to see. So I'm gonna adjust this just to -100 on the y values and positive 100. Means we're going to change the y scale a little bit. Alright, so now I can see that a lot better. And again, proof that both endpoints are going up. And I can see it's bouncing off of the x-axis at -4. Again, it's bouncing because the multiplicity is even. And it's crossing the x-axis at 0 and at 2 because the multiplicities were odd. And that's kind of all you really need to know about multiplicity. Alright, this video is a little bit long, but again, it's just a review thing, so hopefully it wasn't too much. Alright, see you guys later.